Hi, today we are here at my AC coupled Powerwall again, and we are going to upgrade the system. I will show you in a moment what I have now here and what we are going to do. But it's more or less about how the controller is monitoring or managing the battery. So at the moment there is essentially no connection between controller and battery other than one wire which is measuring the battery pack voltage, but that's already it. All other interaction is not available at the moment, but which would in some sort be very important. What we have here is now a very capable controller, and that on a very difficult to manage lithium iron phosphate pack, and in between there is a cheap Chinese Coulombmeter which is giving me some extra information, and all this will be put now together under the hood of the controller. So let me show you quickly in detail the separate individual systems now and what is going to change. This here is now the current status. We have from one side the controller. The controller has a measurement wire to the battery pack and is only getting battery pack voltage. And with that information, and then by switching its components like chargers and inverter, it is trying to estimate the state of charge of the pack in a very sophisticated way. This is only using voltage-based prediction with consideration of other factors like currents drawn by chargers, inverter, etc. And the other system is this battery monitor here. It's a Coulombmeter. It has a shunt here. Here the current is measured, and then the Coulombmeter will calculate state of charge based on energy flow. This one is a Chinese device by Yuntech. It costs around $25 to $30, so it's not that cheap, but it has really big drawbacks. I will tell you why that is and what we are going to do to improve the whole system performance here. So how does the Coulombmeter work? I said already, it is measuring energy flow, but it does not take any specific voltage curves into consideration when it's making its calculations here. So essentially how this works is you tell the meter how big your battery capacity is, and then it will just count up or down and show you the predictive state of charge there. And how exact this works depends on several parameters. One of it is how exact is the entry you made to the meter, that it knows the battery capacity, and the other thing is how exactly can it measure the energy flow. So this will in principle go from 0 to 100 cycle by cycle, and the only way this meter can calibrate is by hitting either 100% or 0%. So if the meter hits 100%, but at the end the charges are still running, because by voltage the battery is actually not yet full, then the meter of course can only stay at 100%, and it will wait until it starts discharging again. And same thing will happen at the down. Once it's reached 0%, but there is still energy in your batteries, the meter can only show 0% until you start charging it again, the pack. But what happens if somebody does not want to charge or discharge always 100%, 0%? Let's say you want to run your pack between 20 and 80%. So you can of course set the starting point of this meter, and if the capacity which you set is correct, it will also of course cycle by cycle stay between your 20 and 80%. But there is a big problem with this kind of meters. and that is that they can never measure energy as exactly. There's something what will happen, and this is called drift. So this meter will then start drifting. In my case, this meter here, the Chinese meter, will drift towards the top end. So if I would run this pack, let's say between 20 and 80% every day, this meter here will drift every cycle between 1 and 2%. This is not an exact thing here. So every cycle it makes, it will arrive at the starting point with a difference of 1 to 2% than the day before. So let's say after 10 days, 2 weeks, it will not cycle between 20 and 80% anymore, it will cycle between 40 and 100, which is of course absolutely inaccurate. You can then of course do a trick and make relative measurements. So you say the capacity between 20 and 80%, this is your 0 to 100%. So you let the meter hit 100 and 0 every time when you actually come to 80% or 20%. But that's not optimal as well, because people want to know exactly how much energy is in their pack. So this is the problem with the Coulombmeters. So then let's talk about voltage-based prediction. Voltage-based prediction, in my opinion, is superior to the Coulombmeter technique, but only if you of course have a chemistry which is predictable and you have a charge curve programmed into your meter. And this is of course not available anymore on the market. You cannot go and buy a battery monitor based on voltage which has an exact charging curve, discharging curve for a standard lithium ion chemistry programmed inside. That's not available, something like this. You have to do this by yourself. You have to use microcontrollers like this here. There is a charge curve stored inside this controller, and it can be used to make voltage-based predictions. But there's a big problem, and that's why these sort of monitors are not used much anymore, and that is lithium iron phosphate. Lithium iron phosphate has essentially 3 problems for voltage-based state of charge prediction, and the number 1 is the nature of the curve in itself. So you have a very flat part between, let's say, 85 and 20% state of charge, and to track that part it would require an extremely sensitive analog to digital converter, which do exist. This monitor also have a very sensitive one, but there's the factor number 2. Factor number 2 is that the chemistry is trying to reach a resting state all the time. So as soon the current is dropping below a C rate of, let's say, around 0.03, something like that, the ions will be more interested to find a place to rest than actually going from anode to cathode. And that makes it very difficult, because the voltages will start changing and floating around. And then there's the third factor, and the third factor in lithium iron phosphate is that the internal resistance, or how easy it is to move ions around, is changing by state of charge. So in a low state of charge, ions can move very easily in this chemistry. But when the state of charge is very high, you need a lot of pressure to move the ions around. So it's getting increasingly difficult. If you make a voltage-based prediction corrected by the current, which then usually have to be done, take voltage differences into account. This is different in a low state of charge than in a high state of charge. So you have to account for all these kind of factors. And of course nobody wants to do this, because if a manufacturer is bringing such a product on the market, the consumers would just complain them why this is not working well. So what we are going to do now, something nobody else can do other than you do it in a DIY project, and this is combining these two methods, and we take the best of each world and we will actually build the best battery monitor for lithium iron phosphate available anywhere. It will be a combination between voltage-based voltage prediction in those areas where it is possible, and this is mostly on the low state of charge side, so below 20% state of charge. We can start mix up those two methods, and then below 15% is actually you can go purely on voltage-based prediction. And then of course in those areas where it's impossible to do so, it will be the Coulombmetric method. And this is what we are going to do. Today's video is about the hardware integration, and then there will be a second video where we will talk about how this is then finally put onto this display in a meaningful way. There's only a couple of things we need to prepare for this build. So what we need is similar to the battery monitor, we need our current sensor, and we will also use the INA 219 for this. But again, we have to modify it. We have to remove the onboard shunt resistor because we will use our own shunt again. This is again a 100 amp 75 millivolts. Then we need our prototyping board to make us a low pass filter again. And this all will be connected again as a I2C device. So I will take this Cat5, this network cable, cut it down and use the 8 wires there. There's 4 pairs of wires inside, and I will use this as an extension cable. And the second thing is we need a switch again. That display, there's also the 4-row display there, LCD display, which already has 3 sub-pages. So I want to use a switch to change the display into a battery monitor mode basically. And for that, you know, I have my own boards there. I2C port, I have another one left. But for the switch we have to use, I have a row of spare pins here, so we can use the ground 5 volts plus one of the digital spare pins here. But we need to build ourselves this as a connection cable and also include a 10K pull down resistor in that wiring. Okay, so let's do that. Okay, I will start with the switch. So as I said, we need 3 connections. So this will be just DuPont connectors for my headers there. I don't like that too much because they usually always have a very flimsy connection, but this is just a switch to change a display mode, so it's nothing critical if the connection is lost sometime. So what we have to do is the wire to ground has to pass over a 10K pull down resistor, so that I have to prepare myself. Okay, let's solder the resistor to the wire, and here I will put a shrink tube over the resistor. And the other side is then going to the digital pin. Solder these now together. So, and this one is then going to the switch. And solder this on. Is now the side with the digital pin and the ground wire, and on the other side I need a pin for the VCC 5 volts. So it's important to be about same length. Okay. And that's it. So we have VCC ground and the digital pin to connect here onto the board. And the other side of the cable is just going to the switch, connecting to the switch, and this is then already done. Okay, the switch is finished. We have the connectors on this side and the button on this side, and everything is covered with shrink wrap, so it should be more durable at the end. This will be installed later inside into the lid of the controller, and we will see that then later. Okay, the next one is, as I said, the sensor. We need to remove the resistor here, the shunt resistor. This is a 0.1 ohm resistor, but we cannot use this as we are using our big shunt. So I will add a little bit solder left and right, and then it will be easy to remove the resistor. If you want to remove components from such a board, always use leaded solder before you try to remove something, because this is lowering the melting temperature very much, and it is then easy with the soldering iron to remove it. I now only need to apply heat on both sides, and then it will go off very easy. You see? If you don't do this, it takes a lot of heat because of the unleaded solder, and you will necessarily heat up the other components, which is of course not good. What I need next is 4 pins of this header for our I2C connection. Okay, so that is my header. On this one I will cut this cable here into half, so that I do have the color codes on each end when I make the extension, that I don't make a mistake with coloring. Okay, so let's build a filter. Someone who knows a little bit more about electronics will actually say that the way I am building this filter is not a low-pass filter. But I have to say that if you look into the reference diagram from the INA 219 chip from Texas Instruments, you will find the filter built like this. Because we are not working here from the reference to ground, we only have a differential voltage here. So I'm actually using a sort of combination of a bypass and low-pass filter. At the bypass filter you use several capacitors because you want to optimize how the bypass filter is reacting to different frequencies. That's why I will actually use 3 capacitors. This filter I will use a 1 microfarad main capacitor, then a 10 nanofarad secondary, and the last capacitor will be a 200 picofarad. Okay, let's solder this. The components are soldered. I'm keeping the legs on, of course, now for the time, because I need them to connect the components with each other, same as traces. Components are connected as they should be, so this will be my wiring to the shunt. I will put the sensor right on top of the filter, like this. So this will make it very compact. Let's solder these 2 last points. The remaining board I will cut, so all what is left is just this small tiny sensor. So far so good. The sensor, this will be its box. and one side will go to the shunt, the other side will go to the controller. So what I need to do now is make me an extension cable. This network cable have to be sacrificed. The advantage when you use I2C devices is that you don't need to transfer raw signals over longer distances. So if you have a sensor which needs to be connected over distance, then this is the perfect solution because you're only transmitting data. Okay, now I have here four twisted pairs, and I will keep those pairs together and use two wires always to connect it with one of these ones. Right, so I have connected each of these twisted pairs with one of my wires here. Then put the shrink tube over it, and this is now the one side of the extension cable. Okay, on the other side I do the same thing with the sensor, and then I will show you when everything is finished. It's already with our current sensor. So this cable should be now long enough to go from the shunt then to the controller. Okay, we can take this all now and bring it to the Powerwall to install it there. What have I done now? I have removed the old monitor and the old shunt, and I put my own shunt here, and next to it the box with the sensor inside, and this is now then going here to the controller. I have pulled this cable in for the sensor, plugged it into the spare I2C connector, and for the other thing I have drilled a 12mm hole for the switch here, and that one I've connected to my spare pins, 5V ground and digital pin 14. Okay, so I will close the box again, and I have to write some rudimentary software to include these current measurements, and then we can upload the code and see if the measurement is done correctly. Right, so the basic code to read out just the shunt is now uploaded. We can now switch the display to the battery monitor, and you can see voltage, state of charge, and here now the shunt current. We now have to wait for the charger turning on, and then we can see if that is working. Okay, both chargers are on now, so let's check what the shunt is saying. And here it is. So we have two chargers, one is a 20, one is a 25 amps, and also the Coulombmeter, it showed a little bit less amps that they're putting out. And here the shunt is saying it. We have now 44.2 amps charging 2318 watts. So that looks very realistic. So what is this going to do for us now? We have now a very strong tool in our hands. We can combine Coulombmetric method with charge curve based methods. And what we can do with that now is we can actually produce a monitor which can self-calibrate. It will show us how accurate it is by comparing the two methods. It is doing in parallel all the time. Because the controller knows when it goes into charge or discharge mode, it will perform a battery capacity test basically at every single cycle. If it has enough data, it will calculate the estimated battery capacity, and I will say every time for this chemistry when we have more than 80% of a cycle, then we will of course again calculate our actual cycles, So a lot of things I still have to wrap my head around what all we can implement here, but that will be my task for the next maybe 1 week. I will now code all the features into the controller, and then I will show you the findings and how everything looks like and what kind of numbers the controller came up with in the next video, in the video part 2. Okay, so that was it for today. The video is already long enough. I hope you found it interesting so far. Please comment, subscribe to the channel, like the video, and I see you next time.